let's put what we learned about the integral test and p-series to use here, and let's try to determine convergence and divergence of a series. So the first one, we have 2 over 3n plus 9. So what we want to do is we say, okay, how do I determine if this is a convergent or divergent series? Well, the sort of the easy thing to try is say the nth term test. So I say I want to take the limit as n goes to infinity 2 over 3n plus 9. So that's 2. This gets really large on bottom, so that goes to 0, so there. So what that doesn't tell me is whether it converges. Do not use the nth term test for convergence. It's a test for divergence. So this is inconclusive. So what we have to do next is, let's try an integral test. So the lazy way to do that is just define a function, f of x, 2 over 3x plus 9. So you just take this, and instead of n's, you replace it with x. Now that's not always going to work, because it may not always be a continuous or decreasing series. So if you look at this, you say, okay, well, where is this thing discontinuous? Well, it's discontinuous if x is negative 3, but we don't care about negative 3 because our series starts at 1. So this thing's going to be continuous the whole way through. Now, is it decreasing? So how do I figure out if it's decreasing? Well, hopefully you recognize this as just some sort of shifts of a function. I mean, this is really that, and this is a scale factor, and this is just a shifted 1 over x, and you know 1 over x is decreasing, and it's just shifted backwards. So hopefully you know that. But let's say you didn't know that. So what you could do is you could say, all right, well, I'm going to take a derivative. F prime of x is I believe it's negative 6 over 3x plus 9 squared. Now if you do this, okay, well that squared is always positive. So what you have is something that's negative for every value of x. Well, if it's negative for every value of x, then you know that it's decreasing over the entire domain, or at least the domain we care about, which is 1 to infinity. So we know that it's both continuous, it's positive, because clearly like this is always going to be positive, and decreasing. So since it's continuous, positive, and decreasing, we can apply the integral test. So now we want to take the integral of f of x dx. So in this particular case, you could take a u sub, you could do whatever you want here, and I think you're going to get its two-thirds natural log of 3x plus 9 from 1 to infinity. Now if you plug in 1 here, it's just natural log of 12, who cares? But if you plug in an infinity, that's going to be like a natural log of infinity. So what this tells me is that this integral diverges. So luckily we're going to get some tools later on that talk about something called the ratio test, and we could use the ratio test to figure out this divergence a lot more quickly. But for now, this is a really good practice for using the integral test. Now our next one is 1 over 6 to the n. So, well, we could do the nth term test for divergence. You say, right, 1 over 6 to the n is, n gets really large, 6 to the n gets really, really large, so 1 over a really, really large number is 0. Now, so that doesn't tell us anything. That's inconclusive. So what we can do is let's try to define a function, f of x equals 1 over 6 to the x. Now, this may be, you may say, okay, well, how do I know that this is a decreasing function? And there are a couple ways to do this. One of the ways to do this is, again, to take a derivative. But to take the derivative of 1 over 6 to the x, which is also 6 to the negative x, then you might want to think about like the e rules and things like that. So that's actually that, e to the negative natural log 6x, which is kind of nasty. So when you take the derivative, negative natural log 6, you get that. And, well, we know that 1 over 6 to the x is always positive, or 6 to the negative x. Either way you want to say it. It's always positive, right? Or at least it is over 1 to infinity. And it is otherwise too, but it's continuous because there's no values here that are going to give you trouble. It's positive because 6 to a power is going to be positive no matter what. So you have a positive, and we just need to continuous, need to know whether it's decreasing. Well, this is a negative number. Natural log of 6 is positive, so negative natural log of 6 is negative. And then we just said that was always positive, so this tells us it's less than 0. So this is a really good example of why it's helpful to just kind of know your basic graphs, your what they call family of functions or parent functions. Because if you did, you wouldn't have to do all this. You could just clearly go, well, clearly it's this, that, or the other. This is a lot of extra effort that you have to do if you don't have those parent functions kind of well established in your memory. So this is kind of good justification why you should maybe do that. Anyway, let's take an integral. So you might ask yourself, how did I know that? How did I know that this antiderivative would be that? Well, it comes from the fact that this is an e to the negative natural log 6. So when I take the antiderivative, it's always the e to something divided by that coefficient. So you get that 6 to the negative x back, and it's divided by that. That's, feel free to go check some standard antiderivative tables, integral tables to verify that. But now we have 1 to infinity. Now, when I have a 1 here, that's 6 to the negative 1, and 1 over negative natural log 6. So that's fine, that's fine. What happens here at infinity, though, as x gets really large, then it's like 6 to the negative x. So that's like 1 over 6 to the x. So that's like this. So that drives down to 0. So what you end up with is 1 over 6 natural log 6. The negative cancels because we actually subtract. You're right, we have this one minus the case of that. So those negatives will cancel. Now this is a positive number. It's finite, which tells me this integral converges. Now, here's the rub. This is great. This is actually a good example of using the integral test because you should already actually know what the series converges to. Which is a geometric series. We would need to rewrite this slightly because we need this thing to be indexed at 0. So we could reindex it with those k's. And then we would get 1/6 times 1 over 1 minus 1/6, which gets us I think it's 1/5, something like that. That doesn't sound right. So it's 1 over 1 minus 1/6. That's 1 over 5/6, 6/5. I mean, then maybe that is right. Maybe it is 1/5. That actually probably is 1/5. So anyway, the point being is all this work, recognizing that it's a geometric series, converges. So don't ever work harder than you have to. This is a really good example, but you could have got there a lot more quickly and not only known that it converged, but actually got what the sum was just by using rules of geometric series.